Hello, I'm Alex Dickens, and I'm back for video one, Monte Carlo localization index. So this is going to be a deep dive into localization and specifically the robotics and Vex robotics component of Monte Carlo localization and how I used it. But going back to localization is, in this context, is finding where the robot is in the field, and it's a subfield of robotic perception. How do robots do this? We use vision, hearing, tactile. If you just look around, you know where you are. It's something we do subconsciously entirely. So something that robots really have to think about. And self-driving cars, they have tons and tons of data points, right? They're working on the very edge case where it's super noisy environment, millions of data points, but still, even though they have all this data, creating a useful structure for the analysis and programming of the car moving around is still extraordinarily difficult. And this is a big difference to competitive robots where people are only using 3 to 5 data points. The programming environment for this slideshow will be in Pro, C++, but this is generalizable to any programming environments like Rust, maybe even Python. It might be a bit harder, but otherwise, it's pretty generalizable to any programming environment. Overall, the goal here is to take incoming sensor data, put it into the robot code, and make a better positional belief. But you'll actually see how we do this is we take the positional belief and feed it back into the robot code along with the sensor data, and we do this hundreds of times per second to make the best idea of where the robot is in the field. I'm just going to do a quick disclaimer here. My solution for this is certainly not perfect. This is just my solution. You should pyramid and find better solutions. And if you do, please share them. I'm more than interested to see what you guys come up with. And I'm really excited that I get to share this and see what other people get come out doing. Okay, so one of the important background components that we need to know is discretization. The real world is continuous, obviously. So let's say you have this like sine wave-like movement on the top here, moving that over to a discrete composition of these 3 data points, it's extremely difficult because the robot doesn't really know what that actual signal looked like. It's just taking a guess, even because it only has the 3 data points. So this is always results in a loss of information. This has to be considered when making these filters. Another thing is the belief. This is where the robot thinks it is. It must be representable by binary, or it must be discrete, so representable by binary. These are just a couple different options. So you can see this is more of a heat map approach. And then you have this Kalman filter where it's a multivariate Gaussian, and then you have particles all over the field to represent different distributions that can happen. Okay, so sensor noise. Sensors have many physical limitations. Often sensors have a lot of noise where the sensor jumps around, and I'm sure you guys have encountered this. And it's pretty difficult to account for in filters because you never know what to trust. You have to kind of trust everything, not so much. And that's pretty pretty difficult to like incorporate into the filters. But that's the whole point of this presentation. So let's get into it. Next, or last thing before we get into it, I guess, is the sensors. So we're going to use LiDAR sensors or time of flight sensor, like single point LiDAR sensors. So this sends out a beam of light and it waits for the response. These are pretty good and easily available in Vex. They provide like 1%-ish error. I would not quote me on that. I've just seen that anecdotally in my evidence. And then motor encoders, these will measure movement of the bot, and IMU to take into account the orientation of the robot. Next, going to some methods that exist, we have the Bayes filter. This is the like overarching idea for a lot of these filters, where you take in this initial belief, you have this last belief, and you have these prediction and update steps. Prediction predicts how the robot has moved in the last time step, and then update actually predicts how the robot, other sensors on the robot say the robot actually moved. So this will be a little more obvious once we go into one of the filters, but it it it's a very good approach to create this iterative nature that works well in robotics and with computers. So what does localization currently look like in Vex? It's kind of complicated. Most teams use the state of the art, I guess, is what I would call this arc-based approach as introduced by the pylons or 5225A in their introduction to position tracking document. This represents the robot's movements as a series of arcs, but it has no self-correction, so if it gets off, you're um, in a pretty bad spot there. The next one, this one's slightly different than the arc-based approach, but it has pose exponentiation. This was introduced by controls engineering and FRC. And you can add self-correction to this as the same as the arc-based approach, but it has no self-correction like built into it. That makes sense. Next is the common filter. This is where the belief is represented at a series of Gaussian distributions. This one can be applied in vector robotics using like the GPS sensor, and it is actually done on board on the GPS sensor, but it's a little bit more difficult to do with the distance sensors, although possible with stuff such as the ensemble common filter, the unscented common filter. Next, and what we're going to use in this presentation is Monte Carlo localization. This is a Bayes filter where each of the possible beliefs, possible positions of the robot is represented with a particle, and it resamples the particles in the update step. It's very widely used in industrial and research robotics and introduced by this guy named Frank Delliert from Carnegie Mellon in 1999. This takes into account all these particles. In this prediction step, you can see it moves with a little bit of noise. It finds the particles that are weighted heavier, and I'll talk about how we find these weights later. And then it resamples the ones that are higher weighted as more likely to be resampled and therefore survive more often. Okay, so the engineering implementation. There's a couple assumptions that I made, and one is that the IMU is completely accurate. The IMU is certainly not completely accurate, as we all know, but using some dampening, it can be pretty well assumed that it gets close enough over the period. It will change by less than a degree, which is a very hard variance to beat, and by adding into the filter the option to like fix orientation, especially with so few sensors like the 4 distance sensors, it's just not gonna increase the accuracy of the filter. Next, the prediction step. I'm going to measure the sensor inputs. These are going to be the like left and right drivetrain movements. And then for each particle, I'm going to add noise to the sensor movements, calculate the translation, and add the translation to the point. And then I'll go into justification for why we add the noise, because this is really, really unintuitive when I learned about it. But basically, we add noise to the robot's movements to allow for it to consider the wide range of possibilities that could have happened in the last hundredth of a second, or whatever you're predicting. How I think about this most effectively is saying the robot said it moved 1 inch, but obviously it didn't move exactly 1 inch. It moved maybe 1 and 100th inch, or maybe it's 1 and 1/10 inch, or zero point 0.9 inches. And by adding a little bit of noise, you can actually consider a lot of different possible variations of how the robot moved. And if you do that on all of the particles, and I have about 500, you get almost every single reasonable case scenario. Not every single one, but you get a lot of variety in all the ways that it could have messed up. And then a quick note on how I add the noise in Vex Robotics. I just use like the standard deviation uniform distributions instead of normal distributions, or the distributions that I really should have used. This is a shortcut so that I could actually get it to run about like 6 times as fast. And I could have gone through a lot of work to fix this, but I found that just doing the uniform distribution worked well enough for my use case, so I kept with it. This is one of those my solution is not the best solution case things here. So this is a part of the code for prediction. This is how I interact with the particle filter, and you can see here that it takes into account the left change and the right change of the drivetrain by taking the current left length and subtracting the left length. To do it, this is doing a secant line approximation for those of you that are familiar with calculus. And then it takes the average of the change on each side of the drivetrain, which is pretty close to actually the center. If you had a wheel in the center of your robot, I chose this shortcut because it was the easiest way that I could just use the motor encoders on both sides of the drivetrain. But there's many ways to do this, even if you have a non-centered forward backwards tracking wheel. You can use something like the pylons-based approach to figure out how the robot has moved. Next, I create these distributions. So one is the average distribution, where I take into account the like length of the drivetrain, how far it's moved laterally, and add this specific value named drivetrain noise. This is what I have a configuration for, and I add and subtract it, so I have a plus and minus basically the drive noise of the robot. And then for the angle, I basically do the same thing. This makes it so that the robot doesn't move perfectly in a straight line for this Euler approximation, and instead moves a little bit to the left or right and a little bit forwards and backwards to add that noise variation. Next, I get the angle from, or the change in angle from the particle filter. This is for pose exponentiation, but is actually not important for this filter, so just ignore this part, sorry. And then for the last part, I use an Euler approximation. What this basically means with this eigen library is that I just take the distance or the predicted distance, taking into account the sensor noise for each of the um, average, which I named noisy non-descriptively, and the angle, and I multiply it by the rotation matrix and the distance, so I can get that Euler approximation of how far the robot has moved. And then the last part for prediction is how I update each of the individual particles. So I have this prediction function here. This is what that dot update is. It's actually I pass in a function that the code later uses to update the particles. So it goes through for each of the particles and it updates the prediction, each of the predictions by adding on the Euler approximation for each of those, and then it'll update the distance since update with one random prediction function norm. This isn't perfectly accurate, but for my case scenario and for all of the Vex case scenario, this will work fairly well for basically predicting how far it's moved since update. And I'll talk about why this is needed a little bit later or right now. So I'll talk about this update step. This basically takes into account that really you don't need to take into all the variety, you need to prune it a little at each time step, and you do this by saying some are weighted higher. You do a systematic sampling, taking the higher weighted ones and cutting out the ones that are lower weighted, and then you use systematic sampling and you rerun that prediction step. So determining if the update is needed, this is a little bit of a wonky thing, but if you didn't do this, I mean, the robot will always be moving, so you could probably get away with it, but the belief would almost instantly converge if you stayed still. And this doesn't necessarily seem like a bad thing. Like if you're sitting still and you're getting good sensor readings, maybe converging is good. But this basically eliminates most of the variety that you had in your filter before. And maybe your sensor readings are wrong. Maybe it's sensing like the pole or another robot. And I think that it's better to just avoid the influence from one reading um, on the robot. So I do this by making that calculate distance of the robot. I just sum up the predicted distance of the robot over all the different time steps. And then I basically say, if the robot's moved more than a certain distance, update then. So this is what that code does. So it says, if the distance sense update is less than the max distance sense update, it'll return and just go on to the next step. And then it also has this time step check. Basically, this just makes it so that if it's like 1 second in between updates, it'll just update in case the sensors didn't like detect small movement. And it'll have a little bit of convergence if you're sitting there for like 3 seconds. Okay, so for weighing the points, I weigh the points on the following equation. The probability that the robot is at X given the sensor readings, and that's what that Z and X stand for. It's a pretty complicated thing, but really you have to say that this means that what is the chance that the robot would be at each specific particle given that the sensor readings that were actually recorded on the robot were recorded. So I do this through this code here where it updates the sensors. This is a little bit of code that takes each sensor that I input into the particle filter and just updates them. What this does is it takes the reading from the Vex sensor. This is one of those shortcuts I had to do for Vex robotics. Communicating with the sensor, even though it doesn't really, it takes a negligible amount of time. If you're doing it 500 times per second for 5 sensors, that's 2,500 gets per, or not even per second, per frame. If you're doing 2,500 requests, it'll just bog down your robot. So if you just take this reading once, since it'll say the same for all of your readings, you'll just get a better belief of the sensor data. I then calculate the total weight. This is used later in the systematic resampling part. And then I loop through each of the particles. So this L is just the length of particles. It's a little shorthand I used with a template in my code, which is all in the description, by the way. And it makes it easier so that I can just do loops like this. So first of all, I check to make sure the particles aren't out of the field. So I have this Boolean function that says if it's out of the field, just put it back in the field at a random place. And sure, I could put it close to the actual distribution, but realistically, if I put it in the field in a random place, if it's out of the field, it'll add more variety. And then especially if your whole distribution just walks out of the field somehow, you want the variety back in there. You want a lot so that the robot will actually converge back onto the better location of where it is. And it'll actually converge in like 3 seconds of driving if you write your filter correctly. Next, I take the particles. So what this is saying is I create a new vector. This is just easier to work with in my code. There's a lot of weird things I did in my code that I don't necessarily wouldn't do again, and this is one of them. Basically, I just make a vector out of it, but the next step I keep. Basically, weighing the particles, I go into this function and I go through each of the sensors and I take the total weight, I set it to 1, and then I go through each of the sensors, calculate the probability of that sensor. That's this p function that I'll discuss later. And I multiply it by the total weight and return that total weight. And that's how I get the weight for each of the particles. And then this total weight again, a little weird that I named the total weight twice in two different functions here, but this just adds all the weights. And this is what's used in the stratified resampling in resample. This is a cheap, randomly sampled point without the chance for a complete belief collapse. So what this means is, let's say you have a couple particles that are very highly weighted, and you just randomly sample, simple random sampling. This is something you can just Google. It's in statistics, where you just randomly sample over and over again. There's actually a bigger chance that you get certain particles more than you really should, and actually hurts the variety in your filter. But if you do system stratified sampling, sorry, and you can Google this as well. I can it'll provide a better description than I will. But you do this approach and you'll get more variety in your filter over time. So for this code, I take all of the particles and I duplicate them so that I can um, I put them into a new array because I'm going to change up the indices of the array through this function. I go through the weight and I do this. So I calculate round weight based off 1 over the average of the function in between 1 and that 1 over the random weight. And what that allows me to do is take that first random value for the stratified resampling, and then I go through and stratified resample all the points. It's a little bit of a messy implementation. I'm sure there's better ones, but this is how I did in my code, so it's just going to showcase it real quick. And then for the prediction, this is something that I think could definitely be improved. But right now, I just took the average of all the points, and this allowed me to figure out where the robot was on the field with that average very, very easily and quickly. I didn't have any problems with this part, so I didn't fix it. Okay, so the next part is creating this point belief that you use in the filter. That's this average that I was talking about. But basically, it's that like you just need 1 point for algorithms such as Ramseti, but we need to create some point belief to be able to use it that way. So I started with an average, and there's more um, methods in literature that I would look at if I did this again, but this approach works really well for vector robotics, so it's what I ended up using. So I'll go over real quick, but basically you just take the sum of all the x and y and you take the average of them. It's a pretty simple approach, and that's what I ended up using. Next, this is more of the complex part, that's more of the implementation. I have this distance sensor model that detects the distance from the field rails and compares them to predicted readings that I'll talk about how I calculate. So predicting the readings to the walls, I use this secant method where I have this, I'm trying to predict this hypotenuse, and I know the distance from the wall for each of the particles from the position of the particle, and the angle is known from the IMU angle. And I use this secant approach, and I'm able to calculate the angle pretty quickly with only one trig function. Going to the update, this is what I talked about earlier, how I just get the distance sensor once, and I get the distance measured. This is a little bit funky code, but the distance sensor doesn't like use an optional if it doesn't get a value. It just records 999 millimeters, 9,999 millimeters. So I have to manually check for that and invalidate my measurement then. And then, and this code here, I can discuss it briefly, but what it used to do is get the object size and if the distance sensor was installed and change it that way. But turns out distance sensor, if it's not installed, it'll just record a bogus value as well that gets caught by that conditional. So I didn't need that anymore. And then the object size variable I used to use, but it changes from plural fields to other competition fields, metal fields, and that just made it not really helpful. I just rather have one implementation that works on all fields instead of changing it up back and forth and back and forth. Next, we have this measured value. So I basically just multiply by this tuning constant and by the unit millimeter. The tuning constant is a value that I experimentally figure out for each of the distance sensors. It's usually between 1 and 3-ish% higher. It overestimates it by 1 and 3%. So I just have to take that into account in my code. And then I calculate the standard deviation just using this bogus number that I base formula that I basically just made up. So this could be done way better, but I found that this gave me a pretty good approximation of the square root for, or standard deviation for the normal distribution of the sensor that I used to predict the probability. So going into that probability, I have this is exit function, and I use optionals in a lot of these places because you're not always going to get a sensor reading, especially from distance sensors. Sometimes they aren't able to see the walls because they're too far away. Just taking that into account in your filter and using like optionals or some null value to take that into account, I found was extremely helpful.